Hello everyone, welcome to lecture 27. So today we will talk about the snow avalanche studies, and this is part of module 7, and module 7 we have this avalanche and glacial lake hazard. So let us start this lecture. So before we go into the details, first let us try to understand what we exactly mean by the avalanche or particularly the snow avalanche, right. So it is a rapid flow of snow down a slope like from a hill or a mountain, right. So here you can see many of you might have seen this kind of figure or the videos in news channel, right. So this is a very dangerous scenario, and if it happens it may cause loss of lives at the higher altitude, right. So to understand the snow avalanche, we need to understand the snowpack characteristics. So the changes in the snow grain size and liquid water content, these are important parameters for avalanche forecasting, right. So here there is two terms, snow grain size and the liquid water content. So here you can see these are the grains of the snow, right. So here you can easily understand this looks like a wet snow, right. So albedo is also an important parameter to assess the snowpack stratigraphy and avalanches, right. So if there is a sudden change in the albedo during the winter, it can cause the formation of ice layer and fresh snowfall will cause an avalanche. So what is happening? Let us say this is the area, right, and here you are having the snowfall, right. So depending upon the grain size and the type of snow, right. So whether it is a dry snow or wet snow or contaminated snow, the albedo which is getting reflected from this surface will be different, right. So let us say here you see, if you consider this particular snow, this is bright, right, but if you consider this part, it looks like dirty snow. So assuming these are two different types of snow, here the albedo will be less, but here albedo will be very high, right. So if there is a change in the albedo, what will happen? There will be change in the absorption of the energy. So energy will be absorbed by the target. So that will change the temperature of this particular snowpack, and because of that this dry snow will become wet and then slowly it will start melting. This is one part of the story. Now albedo is also important parameter to assess the snowpack stratigraphy and avalanche. So what we mean by stratigraphy, that we need to understand. Snowpacks are often characterized by a number of distinct stratigraphic layers. So these are the stratigraphic layers, right. So you can see there is a boundary. I have another image that will help you to understand these layers, right. So here in these stratigraphic layers, the properties are very different, right. So it will vary vertically, and the properties will be density, crystal shape, grain size and hardness, right. So these will be varying across this depth. That will help you to understand how they have been formed and how much they are consistent or they are stable in this particular area. This is another example. Here you can see these are the distinct layers. So these are the stratigraphic layers. They have been formed at different time, right, and between this and this there was a gap in the accumulation. So here you can see the easily 8 layers can be seen, This is what I mean by the stratigraphy, right. And I have a few example for the fresh snow and dirty snow. So, here you can see, you can easily understand I mean to refer this particular location as fresh snow. Even here if you see, these are the fresh snow, right, but here these are the dirty snow or the contaminated one. So, obviously when you have contaminated snow, the energy which is coming from the sun here in terms of solar radiation, that will be absorbed here, because this will not work as a Lambertian surface, right. So, here the reflectance amount will be, let us assume this is 10%, but when we talk about this particular layer, here it may be 95%. So, you see the difference, right. So, here you will have less energy available for changing the temperature of this system, but when we have contaminated snow, we have more energy to change the system's temperature, right. Dry snow and wet snow play distinct role in avalanche studies due to their different properties, right. So, this dry snow and wet snow, understanding the properties and behavior of both dry and wet snow is crucial for avalanche forecasting, hazard assessment and mitigation strategies. So, here you can see the different types of snowfall. So, here you have wet snow, normal snow and dry snow, right. And I have one example of wet and dry snow. So, here you can see this is the wet snow and this, the top layer is basically your dry snow. So, if you want to make a snowball out of this dry snow, you will not be able to make, right. But if you are able to make these snowballs, then those are the wet snow. This is the simple way of understanding dry and wet snow. This is another example. Sometimes when we have the snowfall, we can easily make the snowballs, but sometimes it is not possible. So, that is because of the wet and dry snow. So, if there is a dry snow here and if there is a change in the temperature, we have more solar radiation, then this will change to wet snow, right. And then wet snow will subsequently get melted if temperature is still rising. Dry snow avalanche. So, the formation, let us understand, often forms from newly fallen low density snow or wind deposited snow, right. The bonds between crystal are relatively weak and the characteristics, it can be fast moving and create a large cloud of snow dust. They often involve cohesive slabs of snow breaking off the sliding. The snowpack structure, studying layer of different snow densities and crystal type that can create weak layers. Wind loading, analyzing how wind deposits snow unevenly, creating dangerous cornices and wind slabs. Fracture propagation, researching how cracks initiate and spread through the snowpack. So, this is how we need to understand the dry snow avalanche. Now, we have the wet snow avalanche. So, the formation, it occurs when liquid water is present in the snowpack, typically due to warming temperature, rains or melting. Water lubricates the snow crystal, reducing friction and weakening the bond because of the saturation, right. Then we have characteristic, it tends to be slower moving and heavier than dry snow avalanche. They often involve the entire snowpack sliding down to the ground. So, here we have the liquid water content, melt freeze cycle and hydrodynamic processes. So, in liquid water content, measuring and monitoring the amount of water in the snowpack. In melt freeze cycle, studying how repeated melting and freezing or refreezing affect snowpack stability. In hydrodynamic process, understanding how water flows through the snowpack and influences its strength, right. So, let us try to understand the dry snow avalanche versus wet snow avalanche. So, here you can see the temperature in dry snow, it is less than 0 degree Celsius. So, that is why there is a less chances of having the liquid water here, right. And when we talk about the wet snow avalanche, here temperature is greater than 0 degree or near melting point. That is why this dry snow will become the wet snow and it will be towards the melting. The triggers, snow load, wind, weak layers can trigger this avalanche. Here when we have wet snow avalanche, the melting, rain, warming can affect the process. And the speed here it is very fast because of the dry snow, and you can see the velocity, right. But in wet snow this is slower, 20 to 60 kilometer per hour, whereas here it is 100 to 300 kilometer per hour. The predictability depends on the snowpack structure tied to temperature and melt cycle. So, here the atmospheric parameters are very important. Damage potential, in both the cases you have high potential of damage, right. Now, let us try to understand the application of remote sensing in avalanche studies, particularly in snow avalanche studies. So, let us take the example of optical remote sensing in avalanches. Avalanche debris and its surrounding are typically made of the same material is the biggest obstacle to avalanche detection utilizing electromagnetic snow properties. So, what is happening here, since we are talking about the avalanche, right. So, here you have the snow cover and one part of it is getting avalanched, right. So, why it is happening, that we have understood, it has many other parameters, the snow property, meteorological parameters that affect this process, but ultimately the property of this snow and this snow both are same. So, it is very difficult to identify or monitor this using the optical remote sensing, because in optical both appears similar. Due to its high and consistent reflectance, dry snow appears brighter in the visible range. This reflectance diminishes as albedo drops in older or filthy snow or in snow with bigger grain size. So, if there is contamination of or there is a change in the grain size, the albedo will be changed. Avalanche activity is monitored using automatic time lapsed photography, which offers accurate near real time data, and that will help you to model this disaster. Structure from motion SFM photogrammetry facilitates the creation of detailed 3D model from an array of overlapping images. It is a low cost, easy to learn and extremely portable optical remote sensing approach that competes with lidar scanning in terms of spatial resolution and accuracy. So, earlier we had only this lidar scanning, but nowadays we are also having the portable optical remote sensing approach, where we have very good spatial resolution and the accuracy. So, here you can see some of the example. So, these images will explain the process and the location where we are talking about the avalanche activity, right. Here with optical remote sensing in avalanche, so this particular image is the visualization of the RPAS flight path and a 3D model of avalanche debris generated using the structure from motion technique, right. And this particular image, it is the orthophoto of avalanche debris with its outline interpreted in red. So, this is the boundary of the avalanche, right. Now, let us talk about the TLS, terrestrial laser scanning. So, scan of slope with TLS in both snow free and snow covered situations, detecting mass loss in the starting zone and the slide pathways of released avalanche as well as mass gain in the run out zone. So, this TLS can give you very beautiful images of this location, and that can be used as an input in your study. By measuring snow depth with a TLS before and after a controlled avalanche release, the snow depth of the avalanche debris were obtained, right. So, here you have a few components: monitoring snowpack changes, then pre and post avalanche surface comparison, then avalanche volume estimation, and then finally hazard assessment and mitigation. So, when we talk about the monitoring snowpack changes, we have to detect small scale snow accumulation, settling and compaction. For the pre and post avalanche surface comparison, it helps you to detect the snow erosion and deposition zone. When we say avalanche volume estimation, it will calculate the snow volume displaced by the avalanche. So, that will help you to understand the impact of it in the later part, that is the hazard assessment and mitigation. It identifies terrain feature influencing avalanche behavior, right. So, here you can see the output of TLS scanning of mass gain and mass loss in the snow cover induced by avalanches, right. Now, you might be wondering how it is different from landslide, because in both the processes it is the mass which is coming down the hill slope, right, under the influence of gravity. So, how it is different? So, both involves rapid downslope mass movement of materials under influence of gravity. So, here you can see this is the avalanche and this is the example of landslide. Landslide involves rock, earth or debris, right, that we have seen in the landslide module. But when we talk about the avalanches, it involves snow and ice. So, that is why it is the difference in the material. So, the basic difference is the type of material they have and the type of environment they are in, right. These are the locations which was reported in 1987, and these are possible locations of avalanche activities around the globe. And this is from India. So, we have Karakoram, Western Himalaya, Central Himalaya, Eastern Himalaya. These are the possible locations for avalanches, right. So, let us try to understand the anatomy of the avalanches. So, first we have this crown line, right. So, in the figure you can see the crown line. So, the crown will be always on the top, right. So, that is why we have this crown here and the name crown line we are using, right. So, this is the crown line or fracture line. So, the uppermost point where a slab avalanche separates from the snowpack, right. So, here this will be stagnant, but this whole mass will come down, right. Then we have flanks are the two arms connected by the crown. The orientation is down slope, while the orientation of the crown is across the slope. So, the flank is here, even this will be the flank, right. This is flank, and here you can see post avalanche the debris will be coming to this direction, right, and this is the bed surface of the avalanche. Then we have bed surface that we have understood there. So, this is another avalanche where we have the bed surface here. Inside this is the bed surface, right, and here you have flank, here you have crown, right, and the debris will be here in the downstream or in the downslope. Any material collected by the avalanche in its path may contain timber or rocks if we talk about the large scale avalanches. Then Stotch wall. So, here you can see it is beautifully showing you the Stotch wall. It is the downslope boundary of a slab avalanche. It is the lowest point of the fracture line where the slab releases and slides over the underlying snow. So, this is the Stotch wall, right. So, avalanche path consists of 3 zones, right. So, here we will understand. So, here you can see the size. What is the size of the avalanche? That also matters, whether it is a small scale, whether it is a large scale. So, that is very important. So, in the first zone, the release area where the avalanche begins, right. So, this is the release area. The second zone is the track where the avalanche reaches its maximum velocity. So, here this is the track, right, where it will have the maximum velocity. The third zone is the runout area where the moving snow slows down and stops. So, this is the runout area, right. So, here you can see the features of avalanches. So, avalanches are mostly triggered spontaneously by factors like snow or rain. Because of the change in the temperature, when there is a rainfall, that raindrops also carry certain temperature that will also change the temperature of the glacier system, right, or snow system. Avalanches can also be triggered artificially by things like skiers or explosives, right. So, here you can see, you just see this particular video I am going to play, and here this particular gentleman, he was skiing, and then because of that movement this avalanche got triggered, and you see the scale of this avalanche, right. So, the explosive triggers, that is also possible. So, here hunting down the cornices, right. So, cornices are overhanging ledges of snow that forms on the leeward side of ridge or mountain edge. Here you can see this is the cornices, right. So, this is a mass which is hanging, formed because of the snowfall or the accumulation over the time. They are created by wind transporting and depositing snow, which then builds up over time. It refers to identifying and assessing the risk associated with snow cornices, which are overhanging masses of snow that can break off and cause avalanches. So, here we are going to have the manual blasting to remove this one, right. So, you can see. Then we have the Weisschen Tower. So, here you can see this particular video. This is just to explain you, and these are very nicely created videos. So, that will help you to understand. So, these Weisschen avalanches tower use remote controlled blasting to proactively cause avalanches, right. The control center sends a coded command to the deployment box control system to start blasting. Explosives are available in that particular box in order to cause an avalanche, right. Then we also have artillery methods. So, manually we are firing and then we are triggering this avalanches as and when required. So, there are 3 main forms of avalanches release. So, the first one is the loose snow avalanche, then we have slab avalanche and then gliding avalanche. So, you can see the loose snow avalanche, they are very loose, right. So, they are not very dangerous, you can see, but the slab avalanche, that will be a major chunk of mass that will be causing this particular disaster. Then gliding avalanche. So, here you can see that it is gliding. So, there are multiples of fracture which are available here and they are causing. So, the loose snow avalanche, also known as point release or slough avalanches, begin at a single point or fracture line on a slope and spread out in a cone as they move downhill, right. So, they are moving down the hill. Loose snow avalanche starts with a small mass of cohesionless snow falling on the surface. The initial mass in a loose snow avalanche entrains more snow as it moves downhill, right. So, this will keep on accumulating and then the masses will increase. Then we have slab avalanche. It involves the release of a large cohesive layer of snow. Slab avalanche occurs when an extended weak layer buried within the snowpack fails, right. It is often triggered by skiers or heavy snowfall or temperature change, more dangerous than the loose snow avalanche. This is what we discussed in the previous few slides. Then we have gliding avalanche, release of the entire snow cover as a result of gliding over the ground. The risk of gliding avalanche can easily be identified by the typical fish mouth cracks, right. So, these are the fish mouth cracks. Gliding avalanches fail where the underlying ground is smooth, typically on grassy slope. So, what happens on this grassy slope, you had the more accumulation of the snow and then subsequently change in the temperature will lead to the failure of this particular slab. Cannot be artificially triggered and the steepness is greater than 27 degree, often at low and mid elevation it is found. Glides on a film of water, most often on steep meadow slope, very rarely cause fatalities, right. So, to understand the avalanche problem, so we have divided this into different category, right. So, based on the characteristics. So, from that the potential and behavior of avalanches can be understood. The four main problems are the character, size, location and likelihood. This is what we are going to see here. So, this is a very nice diagram related to avalanche problem. So, here these are the four elements: character, size, location, likelihood. So, you can see the avalanche problem, the character plays a very important role here, right. Then we have location, what is the location of avalanche, then likelihood, what is the probability, and then finally the size of the avalanche, that will help you to understand the disaster or the fatalities caused by this particular avalanche. So, here you can see the different elements or the character. So, here you have loose weight, wind slab, storm slab, gliding, right. The cornices, loose dry, all are listed. So, with this I will end the part 1 of this lecture. We will continue this. Thank you very much.